Okay, so this video is going to lay the groundwork for you understanding electromagnetic waves, alternating current, and it's going to be your step into understanding transformers and also electronics, which is coming soon after this. So we are still on Faraday's law. We are still on magnetic flux and electromagnetic induction, induced voltage. So here we need to remember that a voltage will be induced in the coil when the magnetic flux through the coil changes over time. So this is Faraday's law. So we're going to look again at what happens if you're going to be moving a coil into a magnetic field and out of a magnetic field, and we're going to graph that and learn some properties of electromagnetic waves. So in this video, we're going to be following a coil which is going to be moving at 1 centimeter per second. So each centimeter it moves there is 1 second. That's the speed through which it's going to be moving through that magnetic field. And so we're going to be tracing the following: the change in magnetic flux, which is our thigh, from 0 to 10 seconds. We're going to be looking at the induced EMF, 0 to 10 seconds, and we're going to graph the change in magnetic flux for 0 to 10 seconds, graph the induced EMF, and also look at the direction of the induced current. So this would be Lenz's law. Okay, so let's get into it. So let's look at what happens here between 0 and 1 second. So and keep in mind that the induced voltage is only realized when there's a change in flux, not when there's a flux, but when there's a change in flux over time. So that would be 0 to 1 second. There's no change in flux. There are no magnetic lines cutting through the coil. So we need to think of what's going to happen here to our magnetic flux. So there's not going to be any magnetic flux. There's not going to be any change in magnetic flux, and hence no induced voltage. And if we continue to move the coil, this time we move it into the magnetic field from 1 to 4 seconds. What's going to happen there? There's going to be a magnetic flux, and yes, there's a change. Remember, we started off with 0, and now we have our lines cutting through. So there's a change in magnetic flux there, and hence there's going to be an induced EMF. And if we continue to move in fact, we need to take note that there's an actual increase from our magnetic, the change in magnetic flux is increasing from 0 going upwards in our magnetic flux. And so if we continue to trace the movement of that coil from 4 to 5 seconds, we are going to have there there's going to be a flux, yes, but there's not going to be any change in magnetic flux. As the coil moves across that magnetic field, there is no actual change in magnetic flux. The number of lines that are still cutting through that magnetic the number of lines of magnetic force that are cutting through that coil still remain constant, and hence there's no change in our magnetic flux. So we are saying no change in flux, and hence no induced voltage. This is very important to note here. We have our coil still moving, but yet there's no induced voltage because there is no change in magnetic flux. And then if we move out now from 5 to 8 seconds, what's happening there? Now there's a change, and you can see that at this position our coil doesn't have any lines of force that are cutting through it. Hence, this would be a decrease in our magnetic flux, and this is important to note. And as we continue to move out from 8 to 10 seconds, there there are no lines of force cutting through, and which means that there's no change in magnetic flux, hence no induced voltage. So I hope you understand as we look at that qualitatively there, what you should expect or what's really happening as we move our coil in and out of that magnetic field. This would be similar to what I was showing in the simulation in an earlier video. So we want to do actual calculations here. So we need to take note of those two points where we have our induced magnetic field, induced voltage, sorry. And we need to take note that in the first instance there, 1 second to 4 seconds, the voltage was actually, the magnetic flux was actually increasing, and we should expect our voltage to be increasing. And there's a decrease in magnetic flux in the 5 to 8 seconds. So we'll see in the calculations what really happened there in terms of induced EMF. But take note, there are only 2 points where there's actually an EMF in our coil. Otherwise, for the rest of the times, there is no induced EMF. So let's look at those 2 points, 1 to 4 seconds and 5 to 8 seconds. So if we look at the initial flux that we started off there with, would be zero. There are no lines of magnetic force getting through our coil. And as we moved into, we can calculate our magnetic flux as our area there times our field strength, which is 4 milliteslas, and this would give us our final magnetic flux of 2.4 times 10 to the power negative 6 Webers. So this would be the change. So we're going to say 2.4 times 10 to the power minus 6 minus our 0. So this would be the change that's taking place between 1 and 4 seconds. And what's happening at 5 to 8? So this would be just the reverse of what's happening here. So we are moving out of a magnetic field and we are going back to 0. So you see there's going to be a flux which decreases to 0 as the coil moves out. So this would be just the reverse. So our change in flux is going to be a negative 2.4 times 10 to the power negative 6. Everything else was constant there, only that we are moving our coil out of a magnetic field in the same manner that we moved it into the magnetic field. So there is a change, which is a decrease, a negative 2.4. So if we were to represent this information on a graph, it's going to give us some insight into the nature of electromagnetic waves. So let's graph that change in magnetic flux. Let's graph it. So we are saying at the beginning there we have no change, and as we move into the coil, there's going to be an increase in our change in magnetic flux. And as we move across the magnetic field, we are going to have no change. Our change is going to be constant, and hence as we move out, we're going to realize a decrease in our change in magnetic flux. So that would be the graph. And then as we continue to move away from the magnetic field, there is going to be no change in magnetic flux. So that would be the graph. So as you continue to move it in and out, you're going to have a graph that is similar to that. So we can calculate the induced voltages in those time periods. So 1 to 4 seconds, we had a change in flux of 2.4 times 10 to the power negative 6 Webers. Our n term is just disappearing because we are assuming that the number of turns is 1. Otherwise, you would calculate, considering the number of turns where you multiply by your n. So we are just going to say negative 1 for the n. So over 3 seconds, the change and our induced voltage is negative 8.0 times 10 to the power negative 7. So this would be the induced voltage in the first 4 seconds. And as we move out, where there's a second induced voltage, 5 to 8 seconds, we have our negative 2.4 times 10 to the power negative 6 over 3 seconds. and this will give us our 8.0 times 10 to the power negative 7 voltage volts. So you can see here that the voltage is changing from negative to a positive. So let's see how we can represent that on a graph. So the graph is going to look like that. You're going to have 0 voltage initially, and as you move into where there's that change, you're going to realize that there is a negative 8.0 times 10 to the power negative 7 volts, and as you move across, there is no change in flux and hence no induced voltage. Our voltage is 0, and as you move out, you saw that through our calculations there you have a positive change in your voltage. The induced voltage is going to be positive. So you see there's a change in direction in the current that's going to be induced in that wire, as indicated there by the voltage. So as you continue to move out, no change in magnetic flux and hence no induced voltage. So this would be the nature of the waves that you're going to create if you continue to move your magnet in and out of a magnetic field. So let's also take note of some important things here that are happening. As you move your coil into that magnetic field, you can see that our magnetic lines of force, we have crosses there. That means they are going into the paper. So what happens is that the coil is going to create a magnetic field. Rather, it's going to create a current. The current that's going to be induced in the coil is going to create a magnetic field that is going to act in reverse or opposite to the magnetic field that's shown there of the permanent magnet. So the current induced there is going to be such that the magnetic lines of force are coming out. So the current will create a magnetic field that opposes the magnetic field that is present. And so if you were to use your curl right hand rule, you're going to realize that the current that's going to be induced there is going to be going clockwise, such that the magnetic lines of force created by that coil are going to be moving out of the paper. So it's a law. You have to follow that. It will help you as you try to solve some of the problems. And so this is what's happening as our magnetic flux is increasing as you move your coil into that magnetic field. But as you move it out, what's actually happening is that the magnetic flux is decreasing, and hence what's going to happen is that your coil is going to create a current that will try and counteract that change. It's going to create, so the magnetic lines of force that were going into the paper seem to be decreasing, and your coil is going to create the reverse of that. So the current is going to create a magnetic field that is going to sort of replace those magnetic lines of force, such that the magnetic force that's created there is going to be going into the paper. So the coil is doing the reverse of what is going to create a magnetic field that does the reverse of your permanent magnets there. So the current as it moves out is going to be clockwise. This is actually a law that you have to remember, that the current is going to create a magnetic field that will oppose the magnetic field that is present. So with this, I hope you are going to understand what comes after this, which is the nature of electromagnetic waves. We're going to be talking about rectification of alternating current. So this is alternating current, a current that will be changing direction as you continue to move your coil in and out of that magnetic field.